This is part 4 of the Unit 9 notes. In this video, we are going to be covering 3-step stoichiometry conversions. 3-step stoichiometry conversions occur when you move from the far left of stoichiometry island to the far right of stoichiometry island with any combination of variables, and there are 9 possible variations. So for one example, I could be starting off with the mass of one substance and going to the mass of another. So it would take me 1, 2, 3 conversions in order to get all the way across. I could also start with the mass of substance A and go to volume of substance B, mass of substance A to particles of substance B, or any other combination. In our first conversion, we are going to be going from the grams of one substance to the grams of another. Make sure that you are writing all of these checkpoint solutions into your notebook because they will help you with the key assignments that you will be expected to complete. So to start off with, I'm going to write out my 45.7 grams of ammonium nitrate, and then I'm going to be converting to grams of water. So I have 45.7 grams of ammonium nitrate, which is NH4, NO3. I need to cancel out my grams of ammonium nitrate. On my way to moles of ammonium nitrate. In my middle conversion factor, I am going from moles to moles. So I'm going to cancel out moles of substance A on my way to moles of substance B, which in this instance is water because that's the substance I'm trying to get to. Okay, for the final part, I'm going from moles of substance B, which is my H2O, to the unit that I was actually looking for, which in this example is grams. If you do this correctly, your units should cancel throughout the entire conversion until you're left with the unit that you were actually asked for. So we put all of our units in the correct spot. Now we can start to plug in our numbers. When I'm going between moles and grams, 1 mole is equal to the mass from the periodic table. We have a compound here, so we need to add up 2 nitrogens, because there's 2 of them here, 4 hydrogens, and 3 oxygens. And I need to go 2 after the decimal for each of those masses. So if I were to add all of that up, that would come to 80.06. The mole-to-mole ratio is always based on the balance equation. So here I have 2 for the water and 1 for the ammonium nitrate. Between moles and grams, moles is always 1, and then grams is from the periodic table. So I have 2 hydrogens and 1 oxygen, so that's going to be 18.02. Now a very common mistake for students to initially make here is that they see that there are 2 water molecules here, so they put 2 moles of water here. But when you're going between moles and grams, the moles is always going to be equal to 1. So these coefficients only matter within the mole-to-mole ratio part. From here, I am going to multiply and divide across, and then I'm going to round from my initial significant figures, which were 3. So that's going to come out to 20.6. My unit is grams of H2O. So you should always include your unit and also the element or compound that you are ending with. For our next example, we are going to be starting with liters of substance A, and we are going to grams of substance B. On the International Space Station, exhaled carbon dioxide is removed from the air by passing it through canisters of lithium hydroxide. How many grams of lithium hydroxide are required to remove 500.0 liters of carbon dioxide at standard temperature and pressure? So that's what STP stands for. So I'm going to start by writing out my 500.0 liters of carbon dioxide. Since I'm going from one side of the island to the other side of the island, I do know that it's going to be a 3-step conversion, so I could write all of that out now. I'm going to start by canceling my liters of CO2 on my way to moles of CO2. Then I'm going to cancel out moles of CO2 on my way to moles of the substance that I'm actually looking for, which in this instance is lithium hydroxide. Then I am going to cancel out the moles of lithium hydroxide on my way to grams of lithium hydroxide. Just like before, I'm going to check to confirm that everything is canceling. So the liters of CO2 canceled, moles of CO2, moles of LiOH, and I am left with the thing that they were asking for. So it looks like I set everything up correctly. For my numbers, 1 mole is equal to molar volume, which is 22.4 liters. For my mole ratio, I have 2 moles of lithium hydroxide for every 1 mole of carbon dioxide. For my final step, I have 1 mole, which is equal to the molar mass from the periodic table. So since it's a mass, I'm going to need to add up the grams for each of those elements. So I have 1 lithium, 1 oxygen, and 1 hydrogen. So it's going to add up to 23.95. Now I'm going to multiply and divide across. Based on my original number here, I had 4 significant figures. So that's going to come out to 1069 grams of lithium hydroxide. For my next checkpoint question, we are looking for hydrogen fluoride molecules, which are required to react completely with 75.0 grams of tin. So I'm going from grams of substance A to molecules of substance B. I'm going to write out my 75.0 grams of tin. Tin is Sn. I'm setting up a 3-step conversion. My grams of tin is going to have to cancel out, and grams is connected to moles. My middle section in a 3-step conversion is always moles to moles, so I'm canceling out the moles of my old substance to moles of my new substance, which is the hydrogen fluoride. My final step, I am now canceling out the moles of the hydrogen fluoride out to the molecules of hydrogen fluoride. Grams of tin cancels with grams of tin, moles to moles, moles to moles, and I'm left with molecules. 1 mole is equal to the mass from the periodic table. Here we just have an element, so we don't have to add any up. It's going to be 118.71. The mole to mole part is from the balance equation. So I have 2 moles of HF for every 1 mole of Sn. It's going to be 2 over 1. 1 mole is equal to Avogadro's number, when I'm talking about atoms or molecules. And this time it says molecules because we're talking about a compound. Now for this one, since we have molecules, make sure that you are putting that entire number inside of parentheses since it's scientific notation, because otherwise the order of operations will get mixed up and you will not get the correct answer. So from here, I am going to multiply and divide across. I have 3 significant figures from my 75.0, so that means that my final answer should be 7.61 times 10 to the 23rd. And that's going to be molecules of HF. All right, for our next example, here we are going from liters of substance A to liters of substance B. So it looks like we are starting with 12.2 liters of ammonia gas, and we were trying to find liters of nitrogen gas. So I have 12.2 liters of NH3. I know it's a 3-step conversion because I'm going completely across stoichiometry island. And liters of NH3 is going to be equal to my moles of NH3. The middle section is that mole to mole ratio, so moles of NH3 on my way to moles of something new, which in this instance is nitrogen gas. And then finally moles of N2 out to liters of N2. 1 mole is equal to the molar volume, which is 22.4. We're at standard temperature and pressure again. For nitrogen, I have a 1. For ammonia, I have a 2. And 1 mole is equal to 22.4 because I'm talking about molar volume again. Now, before you plug this into a calculator, you might realize you have 22.4 that you're going to multiply, and you also have 22.4 that you're going to divide. So you can actually kind of skip that because it's going to cancel itself out on the 2 ends of the equation. So really what you just have to do is take your 12.2 and you're going to divide by 2. Now, if you didn't realize that, you divide by 22.4 and then multiply by 22.4. It doesn't really matter. You're going to end up with the same exact answer. I had 3 significant figures at the start, so I'm going to have 3 significant figures in my final answer. I have to add that 0 there in order to have the right number of significant figures. And that is going to be liters of N2. All right, for our next calculation, we are starting with liters of substance A, and we're going to molecules of substance B. So we're starting with liters of sulfur dioxide gas here, so 3.75 liters of SO2. Now I'm trying to find molecules of sulfur, which is S8 in this instance. So I'm going to set up a 3-step conversion. Liters of SO2 to moles of SO2. 1 mole is 22.4 liters. Then I'm going to go from moles of SO2 to moles of S8. That's from the balanced equation. So 1 S8 is equal to 8 SO2s. And then moles of S8 to, we are looking for molecules, so molecules of S8. 1 mole is equal to Avogadro's number. Anytime that you have Avogadro's number, you're going to need those parentheses so that you can make sure that you're following the correct order of operations in your calculator. We're going to multiply across. We need 3 significant figures based on our original number here. So that's going to come out to 1.26 times 10 to the 22nd power. And that is molecules of S8. All right, for our final 3-step stoichiometry example, we have molecule A to molecule B. So in this example, we are starting with 1.2 times 10 to the 24th molecules of sulfur dioxide. So I need to cancel out my molecules of SO2 on my way to moles of SO2. Then I need to cancel out moles of SO2 to moles of my substance B, which is water. And then I'm going to cancel out my moles of substance B out to my molecules of substance B. 1 mole is equal to Avogadro's number. Here I have my mole ratio. So water is a 2. Sulfur dioxide is a 1. And then 1 mole is equal to Avogadro's number again. So this is actually similar to that volume example that we had a while back where we had 22.4 liters on the top and on the bottom. Here we have the same thing. We have Avogadro's number in 2 different places, so they're actually going to cancel out. So if you wanted, you could skip that part in your calculator, since they're going to cancel out to 1 anyway. You do need parentheses around this number, because this is in scientific notation. So you would take 1.2 times 10 to the 24th, and you're just going to multiply that by 2. So we're going to end up with 2.4 times 10 to the 24th molecules of H2O. That concludes part 4 of the Unit 9 notes. Hopefully you wrote out all of those examples and you'll be able to use them as a template when you are working through the practice assignment on Kia. In part 5 of our notes, we are going to be looking at limiting and excess reactant calculations.